Imagine you're standing right in front of a massive, solid steel industrial pipeline. You know for a fact that highly corrosive chemicals flow through this thing every single day, just slowly eating away at the metal from the inside out. One thin spot, one invisible flaw, and you are literally looking at a catastrophic failure. So I have a pretty major question for you. How exactly do you measure a wall you can't see behind? How do you know, with absolute certainty, how thick that steel is without actually cutting it open? Well, in the high-stakes industrial world, you have to measure what you cannot see. You basically have to act as a detective of the unseen.
Welcome to the Explainer. Today, we're taking what might initially look like a dry, standard technical document, the operating manual for the DM5E ultrasonic thickness gauge, and we're going to translate it into a completely fascinating journey. We are going to explore exactly how engineers and inspectors use the literal physics of sound to ensure absolute industrial safety. It's incredibly cool stuff. And this idea brilliantly illustrates our core magic here. You see, ultrasonic thickness measurement isn't about physical rulers or tape measures. It's all about timing. We send an invisible pulse of high-frequency sound straight into a material, wait for it to hit the back wall, and then time exactly how long it takes to bounce back to us. That is what we call the time of flight. We then multiply that time by the known speed of sound through that specific material. It's essentially echolocation, just like a bat, but, we're doing it through solid steel.
So, here is our roadmap for the Explainer today. We're going to quickly cover ultrasonic basics, blind spots and limits, critical accuracy steps, the danger of doubling, mastering the DM5E itself, and finally, safety and service. Let's jump in.
Section 1. Ultrasonic Basics. Seeing sound. Okay, before even touching the device, operators absolutely must understand that a material's unique sound velocity dictates everything. Different materials mean totally different speeds. If you don't grasp how those sound waves behave when they hit the boundary between two different materials, you're essentially flying blind.
Moving on to Section 2, Blind Spots and Limits, Testing Limitations.
Now, as powerful as this technology is, it definitely has boundaries. We really have to draw a hard line between what we know for a fact and what we're only guessing. Information obtained strictly within the limits of your sound beam, that's your truth. But the manual warns operators to exercise extreme caution outside that beam. Why? Because industrial parts have complex geometries. Corrosion causes all these weird overlapping flaws. If you assume an uninspected area is safe just because a spot 2 inches away tested fine, you are taking a massive, massive risk. Making leaps like that requires advanced statistical and probability training, because hidden flaws, they might actually reflect your sound wave before it ever reaches the true back wall.
Section 3. Critical accuracy steps, procedural flow.
So, overcoming those blind spots we just talked about requires absolute, strict adherence to a specific procedural flow. First, you have to perform the probe zero procedure. Seriously, if you don't zero the probe, your readings are completely useless from the jump. Step 2 is calibration. But actually, not just any calibration. You must calibrate the sound velocity on a reference block made of the exact same material you're testing, and ideally it should match the maximum thickness of your test piece. Plus, things like temperature and heat treatments actively change how fast sound travels through a metal. So you calibrate on-site at the same temperature. And step 3, you check that calibration again after you finish testing, just to ensure absolutely nothing drifted.
But, accuracy isn't just digital. It's highly physical. Between the transducer, which is the probe you're physically holding, and the metal itself, you have to use a couplant. Usually this is a specialized gel, and it's kind of an art form. You must use a minimum amount and apply perfectly consistent pressure. Because think about it, if you're pressing really hard on one reading and too lightly on the next, you're actually changing the thickness of that gel layer, and that right there introduces errors into your highly sensitive micromeasurements.
Section 4. The danger of doubling. The illusion.
All right, here we face one of the absolute biggest risks in ultrasonic testing. Under certain conditions, the machine will flat out lie to you. It will display a reading that is twice or even 3 times the actual thickness of the material. Just imagine the real-world consequence of this. You're testing a corroded pipe, you read that it has plenty of thick steel left, but in reality, it's dangerously thin and on the verge of bursting. Scary stuff, right?
So why in the world does this happen? Well, it primarily occurs if you're testing a material that falls below the minimum specified range of your transducer, or if you're using a badly worn probe with a damaged front surface. Essentially, the sound wave bounces back and forth multiple times, creating a second echo, and the machine gets totally confused, just adding those trips together. The golden rule of thumb here? Any reading that comes in under twice the transducer's minimum range must be treated with intense suspicion and verified using other methods or reference blocks.
Section 5. Mastering the DM5E, the tool.
Now that we know all the traps of the unseen world, let's look at the actual instrument designed to navigate them. The DM5E comes in 3 distinct configurations. First, you have the Basic, which handles your standard corrosion thickness measurements. Simple enough? Then you step up to the Dual Multi, which adds specialized dual multi functionality. And at the very top tier, you have the DL, which includes everything plus a highly critical data recorder, which allows you to create files and store vast amounts of reading data right there on the device.
Navigating this device basically means mastering its 4 primary display modes. First up is your measurement mode. This is your home base, showing your thickness and status icons. Second is the probe setup mode, where you select preloaded setups perfectly matched to your specific physical probe. Third is the file mode, which, as we just noted, is exclusive to that top-tier DL version for managing your stored readings. And finally, the configuration mode, where you customize all your instrument controls. The real beauty of this interface is that it actively adapts based on the specific version of the DM5E you're holding.
On a highly practical but super important note regarding the hardware, the device gives you about 100 hours of operating life on just 2 standard AA batteries. The manual highly recommends using well-known battery brands, but pay close attention to this critical warning. You absolutely cannot power or charge this device through its USB port. Seriously, it is for data only, not power. Trying to push power through that port could severely damage your instrument. No one wants to explain that mistake to their boss.
Section 6. Safety and Service Exceptional Stresses.
We've talked a lot about the limits of sound, but we also really have to acknowledge the physical limits of the machine itself. The safety guide is wonderfully, starkly blunt about this. If you even suspect safe operation of your DM5E is no longer possible, you must immediately disconnect the instrument, secure it against unintentional use, and take out the batteries. You don't tinker with it, you don't just cross your fingers and hope it gets better, you shut it down.
So what exactly constitutes unsafe operation? Well, here are the specific conditions. If there are visible damages, obviously. If the software or hardware no longer operates perfectly. And frankly, the manual philosophically admits that no software is ever completely error-free, so you have to be vigilant. You also have to stop if it's been stored in extreme temperatures, high humidity, or corrosive environments for a prolonged time, or if it took a major beating during transport. Exceptional stress on the outside means untrustworthy measurements on the inside.
And remember, this highly sensitive device is strictly for industrial environments. The manual explicitly prohibits any medical applications. It is for steel, not bone. And when the time comes, whether for the batteries or the device itself, disposal has to follow strict environmental regulations. If the device fails, you don't fix it yourself. It must be sent to a designated factory-trained service center.
Which leaves us with this final, provocative thought. We've spent this entire explainer looking at a tool that practically performs magic. I mean, it can see through solid walls. It can predict failures before they happen. But an ultrasonic thickness gauge, no matter how incredibly advanced, cannot think. In the high-stakes world of industrial testing, where a literal millimeter of difference can mean the difference between safety and total disaster, the tool is still only as accurate and as safe as the highly trained human who zeroes the probe, applies the couplant, and interprets the echo. So I'll leave you with this. As our tools for seeing the unseen become more perfect, are we ensuring our human procedures are keeping pace? Thanks for joining me on this explainer, and keep asking the deep questions.